Is anybody here? Brian, can you hear me?
Yes, I can.
Okay. It looks like you're the only one here. So yeah, I'm not sure. I'm not sure what's going on. Normally we have quite a bit more students. Already. Let me start by asking if you have any questions, then we can start by clearing that out. Otherwise, what I had in mind was going through some of these practice problems.
I would like to go through the practice problems. That's fine.
The TA has done quite a few of them, so the plan was to go through some of the problems that that he has not gone through. That being said, given that you're the only one here, we can change that as we go along. The first one I had in mind was problem number 3B. I want to try to see if I can highlight some of the things that, like if I see a problem, how I would go about, like what is there to look out for. This is just like a few tips and tricks on how to read a problem. So 3B, this is about infima and suprema, and so 3B, it says you consider a set. So you'll have points such that. So I'm not going to write here because I'm trying to get across like how I would read the problem. So you'll write something in here, and then you have your t. In this particular case, the variable is called t, and t belongs to the interval 0 to infinity. So then when you see a description like this one, almost irrespectively of whatever I write in here, the trouble is going to be dictated over here on the right hand side. Like the things to look out for is going to be dictated over here on the right hand side. And so you're seeing 2 to infinity. So what comes to mind? Well, it's open around 2. Okay, so this is a potential problem. Right, so we note that this thing here is open. Right, so this means that the set fails compactness. So it fails compactness. And that's important because the points that make it such that you fail compactness, these are trouble points, right? So this is going to be where something is going to happen. If anything is to happen, it's going to be around those points, right? And then you have infinity over here on the right-hand side. Okay, and infinity, this is always a potential problem. So bad things can happen here around 2, and bad things can happen around infinity. Okay, so, and it doesn't really matter what you put in here, whatever problem that you're going to be facing, by looking at the domain and identifying from the very beginning exactly what could be the sticky points. Now, whether or not these will turn out to be trouble points, that depends on the description of the set in here. So let me fill in what is written in the problem formulation. This is t plus 1 divided by t minus 2. All right, so this is a set. We call the set for something, say, called E. Right, and what we want to know is it bounded, unbounded, from above and below? So the first thing that I would do is, I know there's a problem here around 2, there's a potential problem around infinity. There are 2 potential problem points, and we look at the formula now, and indeed, yes, we see here, there is a problem around 2, right? Because when t goes to 2, this thing here goes to 0, and this thing explodes. So what do we, and what happens out in infinity? Well, out in infinity, we're having a t over t situation. So a t over t situation, this is going to be what it'll be converging to 1, right? Because Levitar's rule tells you that the derivative of t, well, that's 1 divided by the derivative of t, that's still 1. So the limit is going to be 1 over 1. So if I were to plot it, we would have explosion around 2. This is when the thing explodes, right? And then we have convergence out here. It will converge to 1. And so it'll look something in between. It will look something in between, but it will converge to 1 out here in infinity, and it will explode in here to plus infinity around 2. Does that make sense to you guys? So what it does in between, this is typically not particularly relevant for the question, right? What we're interested in is it bounded from below? And the answer is yes. It's going to be bounded from below, because whatever happens in between here, it's not going to be unbounded, right? Because there's going to be, even however wiggly it might be in here, it's going to be bounded from below, because, well, there's no possibility for it to explode, right? So this is bounded from below. I think if you work out exactly what this thing here looks like, you actually get that this is a nice function that just decays properly to 1. But for the analysis about being bounded from below or bounded from above, this is what you need. All you need to understand is what happens out here in infinity and what happens here around this point too. And you also see that it is not going to be bounded. It is not bounded from above, right? Because around 2, the thing explodes. So that was some of the first, and then we want to find the max and the min, right? So if you're not bounded from above, right, this part here, this is going to imply that the supremum of E, this is plus infinity. Now, bounded from below, it means that the infimum is going to be this one here. This is going to imply that the infimum, this is a number in R. And so what is the infimum? Well, so to figure that out, now we have to fill in what the function looks like. Okay, so try to plot the function, and the function is decaying. Then you just use that it's decaying t into t plus 1 over t minus 2 is decaying. So what is the smallest value? Well, the smallest value is going to be its limit, like t plus 1 over 2. This is going to be strictly bigger than 1 for all t. T bigger than 2. Decaying, it's bigger than 2. So what are we guessing? We're guessing that the supreme, no, the supremum, the infimum. We already dealt with the supremum, that was infinity. What about the infimum? The infimum is going to be what?
Is it 1?
That's going to be the 1, right? You could ask yourself, like, so one could ask you why. Well, what happens if, say, the infimum would be strictly bigger than 1? We would get a trend. We would get a contradiction. We would get a contradiction. Why would that be? Well, because if the infimum is to be strictly bigger than 1, we would have to have the t plus 1 divided by t minus 2. This would have to dominate this infimum, right? Which is bigger than 1. Because if I would take the limit as t goes to infinity, then on both sides, this would then be bigger than or equal to the infimum of e. And on the other hand, we already argued that it's equal to 1, right? So we get that 1 is strictly bigger than 1. So this doesn't work. And very similarly, if the infimum would be, say the infimum would be strictly less than 1, well then what? Then we can make we can find a an epsilon such that the infimum plus epsilon stays below 1, right? And you'll have that the infimum of e plus epsilon, this would be less than t plus 1 divided by t minus 2. But this is a contradiction now with the infimum already being the biggest low amount. This here is bigger than the infimum over e. Right, so that's a contradiction. So there's not much left. The only thing that is left is the 1. And this is not a min, right? But there's no t inside e such that t plus 1 divided by t minus 2 is equal to 1. Right, so it's not a min. You good so far? Okay, so the next one I wanted to do, there was in the lecture on Wednesday, one of you guys asked if I could do problem number 5. And I talked to the TA and he said he already spent a lot of time doing problem number 5. So because of that, I proposed to do like a compromise. There is a problem towards the end. Find it. There's a problem towards the end. Problem number 7, which is very similar to problem number 5, but not quite the same. So let me try to do that one. So this is quite similar to 5, which was done, which James did. So you're having what you're given is a recursion. You're given the description of AN is defined recursively. So you start out with the first one, that will be A1. A1 is defined as 1. Then AN plus 1 is defined in terms of the previous one. Actually, to highlight it, maybe you should just write out the first couple. So A1 is like that. A2 is equal to, what will it be? The formula says root 2 plus A1. And then you can plug in. So this is going to be the root of 3. And then you have A3. This is the root of 2 plus A2, right? So that will be the square root of 2 plus the square root of 3, and so on. And so the general formula is that if if you're given the previous one, you take it and you stick it into this formula. So that's the recursive. That's the recursion for the ANs. Okay, so you're being asked to do a few things here. You're being asked to prove that it's bounded by 2. So show AN. Well, it's going to be positive. It's a square root, so it's going to be positive. So show that this belongs to 0 to 2, right? I'm going to show a bit more, right? You also want to show that it converges. So this is what brings it back to number 5. Like, let's also show. Let's also show AN converges and find its limit. Yeah, so Brian is saying he has an idea on how to do this. Yeah, let's try to do induction. But the first one, that's clearly bounded by 1. The first one is clearly bounded by 1. So A1 is bounded by 2, right? It starts out at 1. So then the second one, and the second one is the same way, right? So let's try to bound AN plus 1. Well, let's see what it is. So AN plus 1 is root 2 plus AN. And now the square root function is increasing. So if I put a 2 in here, I'm going to get 2 plus 2. And the square root of 4 is 2. So AN is bounded. So up to this point, we have that the ANs are bounded, right? So for example, at this point, we'll be able to use, so knowing here that AN, well, as a sequence is bounded, it sits inside a bounded interval. We can use the Bolzano Weierstrass theorem to extract a convergent subsequence. So you would have A and K. This would be something that would converge. So we can do that without any more analysis. We now know that AN must have at least one convergent subsequence. Okay, we could also, so we could, for example, from this, one thing one could get out of it is this limit up here, right? We could start guessing what this limit would be. Now we know we have a convergent subsequence, so we would know if I use the formula that a and k, this is going to be equal to the recursive formula. So this is a n k plus 1. This is going to be equal to root 2 plus a n k. And now I know that there is a limit. This subsequence here has a limit, right? So this thing here is going to converge to something, L, which is the same thing as 2 plus L. So what will we get here? We will get L squared is equal to 2 plus L. Right, so we solve. What kind of an L would do this? It's a second degree polynomial. It's going to be 2 plus 2 is 4, 2, and this is good. We're going to get 2, right? So the subsequence that's convergent, there's only one choice. It must converge to 2. So we are more greedy. We don't just want a subsequence. We want more. We actually want the sequence itself to converge. So how would one do that? So one could say, how do we ensure that the sequence itself converges? Well, one sufficient condition is monotonicity. So if an is monotone, then an converges, right? And there's no doubt what it converges to. It has to be 2, because any subsequence that converges must have that limit. So if the original sequence converges, it's going to converge to the same limit, right? So it has to converge to 2. So if you can prove monotonicity, so either decreasing or increasing, well, we'll be done. And we can see here that it starts out at 1. So it seems like we should probably try to prove that it's increasing if it's monotone. So let's show that it's monotonically increasing. Okay, so we are saying now that an plus 1 is going to be bigger than an. And how would one go about doing it? Well, again, we will use the recursion. So we will, on the left-hand side, we will put in root 2 plus an. But the claim is that this is bigger than an. Brian is asking me to repeat about monotone convergence, right? So if the sequence is monotone, it converges. Right, so if a sequence, if the sequence converges, it has to converge. If this sequence converges, then there's no choice given that we already established that it has a convergent subsequence. If the sequence itself converges, then there's no choice. The 2 limits must be the same. Because we showed up here that this convergent subsequence, like if there is a convergent subsequence, it has to have the limit 2. Okay, so if the sequence itself would be monotone, then it would converge, and it would have to converge to 2. There would be no choice for it, because any convergent subsequence has a limit 2. Does it make sense, Brian? Okay, good. So how do we prove something like this? But this one here is not bad, right? You have a square. The square root function is increasing, right? We move it to the other side. I get 2 plus an. This is bigger than an squared. So how would all this look like? How would one argue that something like this is true? How would this? So if I would look at the function x being mapped into, say, 2 plus x minus x squared, and x is restricted to be somewhere, x is restricted to be between 0 and 2. How does that look like on a picture? Right, so here I'll have 2, here I'll have 0, here I'll have x. If I take x equal to 0, I'm going to get a 2. And if I take x to be 2, I'm going to get a 0, right? So it's here, it's here. I know it's a parabola that has the legs downwards, right? Because when x is big, so the top point has to be, where does the top point have to be? Like, the top point has to be in between here. I guess it could also be over here. Let's figure out where's the top point. So let's, where does it take its max? If I take the derivative with respect to x of 2x, 2 plus x minus x squared, this is 1 minus 2x. I want to solve this for x hat. That's the maximizer. I'm going to get that x hat is equal to a half. Okay, so its top point sits right here. So then it's a parabola that looks like this. Right, and what I want to show is that for all these x's that are sitting in here, I am strictly positive. I'm bigger than or equal to 0. Right, so that's true. All x's between 0 and 2, this function here is positive. This thing here is, this is okay for an between 0 and 2. Right, and that's where we know it sits. So it's monotone. So it has a limit, and the limit is 2. Questions on this? We all good? Okay. Then the next one I had in mind was, this was a surrogate for number 5 that was being asked for in last lecture. The next one I had in mind was number 6A. 6A, it says compute the limit as n goes to infinity of n times a bunch of things, root 1 plus n 2 divided by n squared minus root 1 minus 4 over n. But so the situation we're facing is what? Well, if I look at the individual terms, I have these 2 square roots. If I look at them individually, 2 divided by n squared, this is going to go to 0. So this first one here is going to go to root of 1, which is 1. So this part here, this is going to converge to 1. The same thing over here, 4 divided by n, this is not n squared, 4 divided by n, this is going to converge to 0, so you're going to get root of 1. So this is going to converge to 1. So then the difference, if I take everything into parentheses, this is going to converge to 0. And then you have n sitting outside, this is going to converge to plus infinity. So the situation we're having is a 0 times infinity situation. And those can be anything, right? This is, who knows what that's going to be. This is our job to figure out. But had we not had this situation, right, had we, for example, had this term not been there, like had it just been the first one, then this would go to 1, and this would go to infinity, then the product would go to infinity. Had we not had the first one, but only the second one, right, this would have gone to -1, and then n would go to infinity, you get something that goes to minus infinity. but now we only have something that goes to 0 times something that goes to infinity, and this can go to whatever. This can go to lots of different things. It's not clear what it goes to, and this is why we're going to try to do the analysis. And so how would one go about doing this? Well, we're going to have something with square roots, and there's a plus. Maybe so what is the rule that comes to mind is very often you'll have these a plus b times a minus b. The mixed terms, you drop out. You just have a squared plus a squared minus b squared. So something like that. This is often helpful. And so what we can do is we can write this here out, multiplying and dividing by the same quantity. So if you swap the minus here to a plus, we could write this here as n, then keep the parentheses, 1 plus 2n squared minus root 1 minus 4 over n, and then multiply and divide by the same quantity, where I swap this minus sign here to a plus, right? So I'll have n downstairs. Will I have n downstairs? I don't think I need an n downstairs. This is not the troublemaker. The troublemaker is these two, so I'll just have those. So I have 1 plus 2 divided by n squared, and then I'll put a plus instead of a minus. So I'll do, and then I'll put the same thing on top. I didn't do anything, I just multiply and divide by 1. And now where the magic happens is when you then multiply these terms together. Because you see over here, that difference here was what made it go to 0. If I put a plus, right, then this would go to 1, and then this would go to 1, I'll get 2. The same thing over here, right? When I have a plus here, so this thing is going to go to 1, and this is going to go to 1. I'm going to get something that goes to 2. So let's try it out. We're going to have our n. We're going to have this term times that one. This is what gives us a square. So we will have a ratio. I should make more space here. Make more space here. So downstairs it's the same. Upstairs is going to change. I'll have the first term times the first term. We're going to get 1 plus 2 over n squared. And then I'll have the other one with a minus sign, minus 1, minus is going to be a plus, 4 divided by n. And then the same stuff downstairs. The stuff downstairs is going to converge to 2, so it's not that problematic. And now I think we should be in much better shape. See the 1 here and the 1 here, you will cancel. And so what am I have n divided by n squared. N squared is going to win, this is going to convert to 0. You'll get a 4. We already argued that the bottom one is going to go to 2. This is going to converge to 4 divided by 2, which is half. We have questions on this 6a here. Awesome. Let's get some more paper. The next one was number 7. We already did. Then number 8. Let's find number 8. Let's find number 8. See how that goes. What do we have? We're looking at n squared plus 1 times cosine of n divided by n to the power 3. So I want to compute the limit. So what you want to do is you want to look for the big terms. Look for the leading order terms. Cosine oscillates. So that's not good for a limit, right? So you cannot write limit of cosine of n, right? So that's not allowed. So whatever you do, don't write this. Brian is suggesting we use the squeeze theorem. I like that very much. What would be your upper squeezer? That's right. Cosine is the absolute value of cosine. So cosine is bounded by 1. So if I take absolute value, so maybe Brian is using this result here. If an converges to 0, what does that imply for this guy? If the absolute value of something goes to 0, then what about a, and where does that go? It also goes to 0. Very good. So we're looking at the absolute value. So this is n squared plus 1 times absolute value of cosine divided by n to the power 3. I want to compute the limit. I want to follow Brian's suggestion that this is bounded above by n squared plus 1 divided by n to the power 3. And where does that go? That goes to 0. Very good. Right, so then I have this property, then you're going to get that one. There's a problem that's very similar. While we add it, maybe we should do that one. If I would do number 9. I do problem number 9. What do we have? 2 times minus 1 to the power n plus 3 divided by root n. Brian, we're getting there. We're getting there. Let's just do this one here is almost the same, right? So what would the limit be here? What would the limit be here? Yeah, I agree, Brian. And what would you get in the limit? Very good, right? You take absolute values. This one here is bounded by 1. Square root of n goes to infinity. You're going to get 0. Let's see the next one. 7, 8, 9. My plan was to do problems 10 and 11. So let's just do 10 and 11 and then seven. So problem number 10. So is it true? So if AN converges to L in R, does the absolute value converge? What do you guys say? Yeah, we proved this in class, but now we have proved so much more, right? Yes, so for any function that is continuous, for any function that is continuous, we would have that f of AN would converge to f of L. So in particular, f of x being the absolute value function. So that's good. What about the other way around? This was number 1. Let's do number 2. If I put absolute values places, the other places, what happens then? So if the absolute value converges, does AN converge? What say you guys? What say you guys? Any guesses? Opinions? What could happen here is that AN could oscillate. So if AN oscillates, so you could have, so the answer is no. You could have that AN, for example, would be something like -1 to the n. That does not converge. That does not converge in R. But if you take the absolute value, you get 1. So the absolute value converges to 1 because it's a constant sequence. And but the original sequence before you took absolute value, that would not converge. That would oscillate. The third one is about, now we move into series. So say that the series converges. So that this thing here converge in R. It does the series when I take absolute value. What say you guys? Fernando says no. Do you have a good example, Fernando? Yeah, very good. This is wonderful, wonderful. So, so consider 1 minus 1 to the power k divided by k. This converges. I actually wrote down where you can find this. This converges. This here is lecture 9. This is exercise 271. This object here converges, but if I take absolute value, this one here, this converges in R. This thing here converges to plus infinity. And this is something we talked about early on. This is lecture 5. And then there's the last one. What happens if I swap the two statements? So say that the absolute value converges. So that this converges in R. Does, when I drop the absolute value, does this one converge? And Brian is saying yes. This is a triangle inequality argument, right? This is a triangle inequality argument. We done that. We did that in I forget what lecture. I forget what the number was. Absolute convergence theorem. Yeah, so I think it's somewhere in here. I forget what lecture it was. I think it's one of the lectures we did in person. Where are the conditional convergence sequences? Down here, this one. if this thing here converges, then that sequence converges as well. And over here, there is going to be something with a triangle inequality. Are there any questions on these steps here? This series here always converges if you're willing to allow for plus infinity over here. This is monotonically increasing. You have positive numbers, you're adding up more and more. This, as a function of n, this series here increases. So it always converges when you allow for the value plus infinity as a limit. So here it specifically said that it converges in R. So it does not allow for this plus infinity limit. Are there any questions on what we have here? Okay, then the next one, I think this was the one that Brian was asking for. Can we please do number 11? So I'll put a couple of questions in here about cardinality. There's going to be a question on your midterm next week about cardinality. So this might be a good idea to do. So problem 11. So we have countable sets. So AN is a countable set. So we have, right, so right. What that means is that I can find, I call them in the solution, I call them tau n. Tau n that goes from the natural, like countability means that you can find a function that goes from the natural numbers, takes values in AM, which is onto. So this is surjective. So that's what it means. So that's what AN means. So it's we have a sequence of them, a countable sequence for each n. So I can find for each set, I can find a map that goes from the natural numbers. It takes values inside AN, which is onto. Okay, so that's an ingredient, right? So the question is, does there exist a map? Does there exist a G which goes from the natural numbers over on to the union? We have this AN for each n. Does there exist a function which is onto? So this is so you're taking a countable union of countable sets. Is that still countable? So in words, is any countable union of countable sets again countable? Brian says yes, and this is correct. This is yes. Okay, so then we have to create it. So let's create such a G. We have G's domain is n, its codomain is this union, and it has to be onto. So the way that I propose to do it in the solution, I'm not saying this is the only way to solve this problem at all. I'm saying this is just one way to do it. So first we need to use something about I have n. Can I map n into n squared? So I'm claiming that there exists a function if that goes from n into n squared, which is onto. I'm hoping that everybody is okay with that. Is that something that we feel comfortable about? N and n squared are about the same. How would one go about doing it? Right? You could just, how could one do this? What kind of a function f you could use if I would arrange n squared as so I'll write 1, 2, 3, 4. Then I have 1, 2, 3. This here is my plot of n cross n, and I want to be able to write everything in this matrix in terms of natural numbers, right? So what could I put here? What could be what could get mapped into 1.1? So I want to have f of 1. That will give me 1.1. What could I put here? So here I could put 1 in the corner, then I could put 2 here. So I have that f of 2 would be normally take rows first, right? So it's 1 and then 2. And I could put 3 here, 4, 5, 6, and I could sneak around. We have seen this in class many times. So this I can do. I can find a function that goes from n into n squared, which is onto. And here's one way to create it. Are we good on this creation of a function that goes from n into n squared, which is onto? Do the snake thing around in the matrix. We've done something like this with Q. So you would list ratios between them, and then you would have the ratio between 1 and 1 would be the first natural number, and then 2 and 1 would be the second one, and so on. And this would be the same. This is how we would show that Q was this is how we would show that Q was countable. So we got that one. And now how do we proceed? Well, so now we have a function. So we're going to write. So we write f of n. We're going to write this. Well, it's going to take. It's a two-dimensional object. So we're going to write this here as f1 of n, right, and f2 of n. So what's the claim? We have a g here. We have a g here. This is our goal. Let's create such a g. So the claim is that when I evaluate g at a point n, the way that I'm going to do it is that I'm going to take, I have my tals. Those are the ones that are surjective from n into an. Okay, so I'm going to take tal and put in the first coordinate, f1. Right, that was the first one. Tau n, I need to evaluate it. This is a function, right? So for each n, I'm going to get a function. So I need to evaluate it at a natural number. I'm going to evaluate tau n at f2 of n. Claim that this one here works. So take a natural number, plug the natural number into this f, which has the property that is onto. And then I'm going to get f1 and f2. I take f1, pick out the tau that corresponds to that f1, and evaluate that tau at f2. So the claim is that this thing here works. And why would we see that? How would we see that? Well, we have to prove that it's onto. So that means if you give me anything over here, then I can find a natural number. So when I put that natural number into the function, I'm going to get that anything. Right, so what we're going to do is we're going to let an x over in the codomain be arbitrary. So the codomain was this union and be arbitrary. So what we need to show, we need to find, I need to find, like, I'm going to call it a k star in the natural numbers, such that when I take that k star, stick it into G, I'm going to get exactly x. I'm claiming that this function here has that property. Okay, so let me show how it's onto. Pick anything in the codomain. Now show you can find something in the domain, such that when you take that thing in the domain, stick it into your function, you're going to get exactly that arbitrary thing that you had started out with in the codomain. Okay, so how do we create this k star? Well, x is in the union. So because x is in the union, because it belongs to the union, there must be there's some set, right? It belongs to a union. There is at least one of these sets that x is in. There is some n star. There's some n star such that x belongs to that a n star. Right, because if I am in a union, what does it mean? You're going to be somewhere. Okay, what else do I have? I have my tors. So if I'm looking at tor in star, that is onto. Okay, so because tor in star, well, he goes from the natural numbers into an star in an onto fashion. Because this is onto, right? There exists a point. Let's call it m star. This is a point in the domain such that when I take tor n star and I plug in m star, I'm gonna get exactly x. Okay, so what do I have now? I have n and m star. What remains to be used is that 2 points. I have n star is a net, n star is a natural number, m star is a natural number. So what remains to be used is that we also have that f, right? It goes from n into n squared. And if I look at n star, m star, this is a point there, right? So that's a point in the codomain. So there exists a k star in the natural numbers. So when I plug it into f, I miraculously get these. Right? This is because f was onto. And then I'm done, because right? Because f here was equal to f1 of k star, f2 of k star. So I have f1 of k star is n star, if 2 of k star is m star, and then I get the property over here. Just plug it in now. G of k star is equal to tau if 1 of k star evaluated at if 2 of k star. Use the properties we had here. This was tau of n star evaluated at m star, but that was exactly my x up here. Any questions on this part? Brian, you were the one that asked about it. Could you follow the argument? Should we do it one more time? Nothing wrong with going through something a few times. This is the notation, I think. The notation is the thing that's the hardest, right? So it takes 2 ingredients. The 2 ingredients. So the first one is right tau n. This is a function that goes from the natural numbers over to these sets an, and this is onto. Right. So any x in an. So for any x, any point over here, there exists some number. I don't know what to call it. There exists a natural number such that tau n of a gives me that x. That's what it means to be onto, right? This is onto for any the sets here, the index by n. Right, so these functions here, there's a collection of, right? There's one for each set. So that's ingredient number 1. There's also a second ingredient. We need to know that n can be mapped onto n squared. And here I'll call that function for f. So again, so for a point, it's called n m. So for any point in the codomain, I can find something in the domain. So it's called k, such that when I take that k, stick it into f, I'm going to get n over m. Could we follow this, everybody? So this one here is good. Okay, so now we have a collection of functions called tau1, tau2, tau3, right? And then we have this f. What we want to do is we want to create g. We want to create g going from n and then over into that union of these ans, which is onto. Right, so we need to create a G such that it's onto, right? So for any point, let's call it X over in the union, we must have that we must have a K over in the domain such that when I take that point, plug it into my function, out pops X. Right, so these are the two things that we have. This is the thing that we need to create. Is that clear? Right, Brian says yes. What about the rest of you guys? Is it clear to the rest of you too? Okay, so how would one go about doing it? Well, what I proposed to do was that start out using this property that we have here. If I belong to a union, X belongs to a union, there must be some point in the index. There must be some n star, at least one, such that X is in that set. Because what does it mean to be in a union? Well, if you are in a union, it means that you are somewhere in those sets that we take in the union of. You could be many places, but you're at least somewhere. Right, so that's what it means to be in a union, right? There is at least one point such that you're inside that set. But then we use, what do we use? We use you use one. So I have my n star now, right? So then you use one to get a point. It's called a star, such that tau in evaluated at a star. This is exactly your X. And this a star, where does he belong? He belongs to n. Then I can use 2. We can use 2 to what? Now I have 2 points. I have an n star and an a star. I have an n star and an a star. So you use 2 to find a k star, such that f of k star would give me what? It will give me n star and a star. That's because f is onto. Right? So you give me any two natural numbers here, n star and a star. You give me any two natural numbers. The function is onto, so I can find something in that function's domain that will take me to exactly that point. Are we good so far? So now it's just a question of combining these things. So if you have my k star, this is out in the natural numbers. This is the thing that comes here. There exists a k in the natural numbers. This belongs to n. And it gets mapped over into n squared. Actually, n star and a star is something inside n star, something into, but this belongs to n squared. So what should I call my function then? Well, what was our definition? What's the definition of G here? G was what we had. So if I evaluate, that's my function. So I'll evaluate G at this this point. What would it be equal to? Well, by definition, it would be equal to tau and then F1 of K star evaluated at F2 of K star. This one here, this is the definition of G. Okay, so now what remains is, what is F1 of K star? Well, it's just the first entry. Like F is a function that takes values in a two-dimensional space. So F will have two coordinates, F1 and F2. Because it would be tau, and then it's the first coordinate. When you evaluate at K star, that's going to be n star. That's my function. Okay, and what point do I evaluate it in? Well, that's going to be the second coordinate. This is going to be the A star. So what we're using here is nothing else, and we're just saying that F evaluated at point K. This is simply written as F1 of K, F2 of K. Just as if you would have a function that would take values in R3, then you'll be able to write the values that it takes as a three-dimensional vector. And now what is this point here? Well, that's what we worked so hard for, right? That's our X. And so given an X, I created myself a K star such that when I plug the K star in, I get exactly X. Did that help a little bit more, Brian? So what did it show? Well, it showed that, I mean, the very beginning was, does there exist a function such that this is onto? And the answer was yes, right? Because we had to create this, if we were able to create a function G such that this would be true, then, I mean, does it mean it's, yeah, this is what it means to be countable. A set is countable if you can, I mean, if you can hit this thing here in an onto fashion with natural numbers. That's what it means to be countable. Right, so maybe this was a confusion. So what does it mean? What does it mean for X to be countable? Is that the question? Well, it means that there exists a function from the natural numbers over to X that is onto. Right, so X equal to Q, X equal to Z, X equal to the union of, say, the natural numbers, or X equals to the union of Q countably many times. They are all countable. X equal to R is not. I don't know, maybe these examples here are not good, but we could have something like, I wanted to put something more specific in here. Let me try to do something like, try to take like n over these ANs. So let's say that AN, this is defined to be n plus 1, and so on. Would that work? No, that's also not so interesting. So let me just keep it arbitrary, countable. AN countable. And that's the one we just did. But so to be countable just means that you can be put, that the natural numbers can hit you in an onto fashion. Alrighty, we are out of time. Are there any more questions before we wish each other a good weekend? I should say, so next week, office hours, Tuesday at 2 p.m. and no office hours Thursday. Brian is asking what we should expect, but I mean, there will be something about cardinality, right? So there will be such, you could have been asked a question like this one. You could have been asked, is n squared countable? Is q squared countable? Is q times r countable? You could be asked, is r countable? Is the cardinality of r and r squared the same? So can you find an onto function that goes from r onto r2? Create a set that has cardinality that is strictly bigger than r. So lots of these things have been discussed and proven either in the lectures or in your homework. Yeah, anything else? I will see you guys on Tuesday then. Have a good weekend.